Hey guys, today we're going to work the study guide for chapters 13 through 16. So starting with chapter 13, our first question here says, true or false, planets in our solar system orbit the sun in circular orbits? That is false. They're in elliptical orbits, which are like stretched out circles with the sun at one focus point. All right, the second one says, what is the force between a 1 kilogram sphere and a 5 kilogram sphere whose centers of mass are 2.5 meters apart? All right, so to do this problem, we just use our formula. We know the force of gravity is equal to our constant g times the product of the masses divided by the distance between their centers of mass squared, at least if they're spheres. And so we just plug in our numbers here. And if you do that, then you'll get 5.34 newtons. So that's the force between these two objects. Our third question says, under what circumstances does an item in a gravitational field have a negative energy? It has a negative energy if it is bound to the object that is producing the gravitational field. So in other words, it also has a negative energy if its potential energy, so remember the formula for gravitational potential energy has a minus sign in it. If that potential energy in absolute value is larger than its kinetic energy, then its total energy will be negative. Right? When can one approximate gravity as a constant force? So if one is under the influence of gravity due to some large gravitating body like a star or a planet, then the force of gravity is approximately constant as long as you are relatively close to the radius of that body. So for instance, if you're very close to the surface of the Earth, then the acceleration due to gravity we know is 9.81 meters per second squared. And as long as you're only a little bit off the surface, that approximation is very good. Right, true or false, the Earth moves at a constant velocity relative to the sun in its orbit around the sun. That is false. So like we said, the Earth is in an elliptical orbit around the sun. So that looks something like this. So the sun is at one of the foci here. So the Earth travels around in this ellipse, and it moves faster the closer it is to the sun. So that's because angular momentum is conserved. So we know our formula for angular momentum is r cross p. If we don't care about the vector part and we just want a number, then it's the part of r that's perpendicular to the momentum times the momentum. So for over here, our distance from the sun is smaller, and so to compensate, our momentum has to be larger. So the mass of the Earth is constant all the way. So the only way for the momentum to become larger is if its velocity increases. So that is false. The velocity of the Earth is not constant in its orbit. Okay, our next one says, a satellite revolves around the Earth in a circular orbit of distance 1,000 kilometers above the surface of the Earth. What is its period? Okay. Well, there is an equation that we can use directly for the period, but let's actually derive it so we can see where it comes from. So we know the force on our satellite is equal to our gravitational constant times the mass of the Earth times the mass of our satellite divided by the distance between their centers of masses squared. Okay. So this is not the distance from the surface of the Earth, but the distance from the center of the Earth. And because the satellite is moving in a circle, that must be equal to the centripetal force, which you'll recall is given by mv squared over r. Okay. So if we solve this for the velocity, and the velocity is, it's plus or minus, but we don't care about the direction, so I'll drop that. It's the square root of g times mass of the Earth divided by the distance between the satellite and the center of Earth and the center of mass of the Earth. Now, because the velocity is constant, it's also equal to the distance divided by the time. So since it's moving in a circle in one period, so in one full rotation around the Earth, it travels a distance of 2 pi times the radius of the circle, which is the same r here, the distance to the center of mass of the Earth, divided by the period. So this has to be equal to the same thing here. So if we solve for the period, then we'll see that it's equal to 2 pi times the square root of that distance. Oops. That distance cubed divided by g times the mass of the Earth. This is all under the square root. Okay, so this formula is on the formula sheet, and you could just use it directly. And if you plug in our numbers, so one thing to note, like I said, this is not just that 1,000 kilometers. This is that 1,000 kilometers, which in meters is 1,000,000 meters, plus the radius of the Earth. So I would give you this on the test. And so if you plug that in here, then we'll see. I'd also give you the mass of the Earth. That our period is 6,310 seconds, which is roughly 1.75 hours. Okay. All right. Now we also want to know the velocity. So to find the velocity, we could just use this equation. So if you plug in numbers, then we'll find that the velocity is 7,350 meters per second. Okay, now we also want to know the total energy of the satellite. So remember, the energy of any object is equal to its kinetic energy plus its potential energy. So we know kinetic energy is 1/2 our mass times our velocity squared. And our gravitational potential energy has this form. It's negative our gravitational constant, the product of our masses, so in this case, the mass of the Earth times the mass of the satellite divided by the distance. So once again, this is the distance between the centers of mass. And notice it's not squared here. It's just to the power of 1. Okay, so this is what I was talking about before. This is negative. So if this term is bigger than our kinetic energy term, then the total energy will be negative. If it is negative, that means it's bound to that object. So if we use the velocity that we found up here, and we use for r, use our 1,000 kilometers plus the radius of the Earth, then we'll find that the total energy is minus 1.35 times 10 to the 10 joules. So it's negative because our satellite is bound to the Earth. It doesn't have enough energy to escape the Earth and move off to infinity. All right, so that's it for the short answer questions. Now for some long answer questions. All right, so starting with 1, an alien planet has a mass of this, and it's in a circular orbit around its star, which has this mass, and the radius of the orbit is this thing. So the radius of the orbit is the distance from the center of mass of the planet to the center mass of the star. Now, normally stars and planets are so far apart that it doesn't really matter if you add the radii of the star and the planet, but whatever. In theory, the radius of the orbit should have those things in it. And so we want to know what the force between the star and the planet is and what the acceleration of the planet is. Okay, well, we know the force of gravity. Let's do it down here. The force of gravity is equal to this thing. So it's the product of them. So I'll call the mass of the planet just m and the mass of the star, capital M sub s, divided by the distance squared. Okay, so if we plug in our numbers, all the numbers are given in the problem. This is 9.96 times 10 to the 22 newtons. So very large, but also the planet and the sun are extremely massive. So that makes sense. Now we also want to find the acceleration of our planet. So the force on our planet is this thing, but we also know from Newton's second law that the net force is always equal to mass times acceleration. So the acceleration of our planet is our force here divided by its mass. So that's 1.36 times 10 to the minus 2 meters per second squared. So notice, even though the force is very large, the acceleration is still relatively small. That's just because of how massive the planet is. All right, so the next question asks, what are the period, velocity, and total energy of the planet? All right, so we already derived our equation for the period. It's that, oops. It's this thing. Yep, and so times 2 pi. So if you plug in your numbers here, then we'll find that the period is 1.61 times 10 to the 7 seconds, or in a more familiar term, this is roughly 186 days. So this is the time that it takes for the planet to take one full trip around the star. Okay, now we also wanted to know the velocity of our planet. But because it's moving in a circle, its acceleration must be equal to the centripetal acceleration. We already calculated our acceleration up here. So if we plug this in here and we use the radius over orbit, we can find that the velocity is plus or minus, but once again, we don't care about the direction. It's 3.49 times 10 to the 4 meters per second. So even though the acceleration is very small, the velocity is still pretty huge, right? This is on the order of 10,000. Okay, that's just because our distance is very large. And we also wanted to know the total energy. So we just do the same thing that we did before. Our energy is equal to our kinetic energy plus our potential energy. So this is 1/2 mv squared minus g times the product of the masses divided by the distance. If we plug our numbers in here, it's minus 4.44 times 10 to the 33 joules. So it's minus once again, because our planet is bound to our star. All right, so our next part says, a group of aliens wish to terraform the planet, and their first task is to decrease the temperature by increasing the distance between the star and the planet. They successfully moved the planet to a new circular orbit of this radius. And what are the new period, velocity, and total energy? Well, we just redo everything that we did before with our new numbers. So it's still going in a circle, so its acceleration is still the centripetal acceleration. And this is equal to the force divided by the mass. So if we take our gravitational force and divide by the mass, we just don't have the mass of our actual planet here. But otherwise it looks the same. So if you solve for the velocity here, it's 5.64 times 10 to the 3 meters per second. So it's much slower now because the distance has increased. The velocity is also equal to the distance over time. So in one full rotation, it has a distance of the circumference, and that happens in one period. So if we invert this, we can find the period. You could also use the formula that we used before. It's the same thing. So if we plug our numbers in here, this is 3.81 times 10 to the 9 seconds, or roughly 121 years. So by moving years, by moving the planet out this distance, its period has increased dramatically. So for one full rotation around its sun, that takes 121 years. Okay. So now we want to know the total energy again. So we do the same thing. It's our kinetic energy plus our potential energy. And with our new radius and our new velocity, this is equal to minus 1.16 times 10 to the 32 joules. Okay, so it's still negative because it's still bound to our sun. And finally, we want to know how much work gravity did to the planet. Okay, so the work done by a conservative force is equal to minus the change in the potential energy. Gravity is a conservative force, so we have a potential. And so we just have to calculate minus the change in the potential energy. And so if we do that, we have minus from this minus, and then the actual potential energy also has a minus. And so it has the form minus G times the product of our masses divided by R. And so since we have a change, we'll use the final R. So this is the distance that we ended with. And then we subtract from that our potential energy initially. So we use our initial R this time. And if you plug your numbers in, then you'll find that this is minus 8.67 times 10 to the 33 joules. It's negative because we're moving the planet away from the direction that gravity naturally wants to pull it, right? Gravity wants to pull the planet toward the sun, but we're moving it away from the sun. That's our next one. All right, that's it. So now we can move on to chapter 14. That's all we have to worry about with gravity. All right, our first question says, under what condition will an object float in a fluid? It will float if its density, the object's density, is less than the fluid's density. Similarly, it will sink if its density is more than the fluid's density. All right, our second question says, the wind puts a force of 100 newtons on one side of a cube with side length 0.25 meters, such that the wind hits a single face of the cube. What pressure does the wind exert? Okay, well, we know that pressure is given by force over area. So we know the force that our wind is putting, and it's putting it on one face of the cube. So we just divide, we take that force, it was 100 newtons, and divide by the area of that face of the cube. So the face of a cube is just a square, side length S. It has an area of S squared. So our side length was 0.25 meters. So we take this thing and we square it. And so our pressure then is 1600 pascals. So this is the unit for pressure. Remember that 1 Pascal is the same as 1 Newton per meter square. Okay. Our next problem says a fluid with constant density of this is placed in a container 2 meters high and is open to the air at sea level. What is the pressure at the bottom of the container? Okay, well, we know that pressure in a fluid is given by the pressure at the top of the fluid plus the density of the fluid times the acceleration due to gravity times the depth. So as long as our density is constant, this is the formula for the pressure at some depth h. If it's not constant, then there's a derivative formula, but I won't give you one like that. Okay, So everything is given in the problem except for this. What is the pressure at the top of the fluid? So it doesn't say that anywhere here, but it does say that it's open to the air at sea level. So the air at sea level has what's called atmospheric pressure, and atmospheric pressure is 1.01 times 10 to the 5th pascals. So we'll use this over and over again. It'll be in the equation sheet, I'll tell you this, but we will need to know it. So now that we know what fits in here, the rest of these numbers are given in our problem and we know what G is. So if we plug them in, then we'll find that the pressure at the bottom of this 2-meter container is 1.5 times 10 to the 5th pascals. All right, easy enough. All right, our next question says, true or false, a fluid with constant density that obeys Bernoulli's equation flowing through a pipe can have more volume of fluid entering one end of the pipe per second than exiting the other end of the pipe. So this is false because of the continuity equation. So as long as the density is constant, the continuity equation tells us that the cross-sectional area through which a fluid flows, so it's going through a pipe, this will be the area of the pipe, times the velocity is a constant. So this is another way of saying that the volume rate, the amount of fluid, the volume of fluid that's coming in per second is constant. So if there's 1 cubic meter coming in per second on one side of the pipe, it also has to leave at any other place later in the pipe. So that is false. All right, our next one says true or false. A fluid with constant density that obeys Bernoulli's equation flowing through a pipe can have more mass of fluid entering one end of the pipe per second than exiting the other end of the pipe. This is also false. Our more general form of the continuity equation that does not assume that density is constant says that the density times the cross-sectional area times the velocity is constant. So if you look at the units here, this is in kilograms per second. So the rate at which mass enters the pipe has to be the same as the rate at which mass exits the pipe. So this is also false. So notice that both of those things are constant as long as the density is constant. If the density can change, then you could have some fluid that gets more or less dense at a different point in the pipe, but we won't worry about that. Okay, our next question says a 0.5 kilogram sphere of radius 12 centimeters is placed in pure water. Does it float? So we know an object floats in a fluid if its density is less than the density of the fluid. So pure water has a density that we'll have to use over and over again. It'll be on the equation sheet, but you'll use it so often you'll probably remember it. It's 1,000 kilograms per meters cubed. So this is the density of pure water. Water coming out of the tap or water in the ocean or something will be slightly different. But if you have pure water without anything dissolved in it, this is its density. Okay, so we have to find the density of our object and compare it to that density. So it has a mass of 0.5 kilograms and it's a sphere of radius 12 centimeters. Okay, so we know that density is given by mass over volume. We know our mass, it's 0.5 kilograms. And it's a sphere. We know the volume of a sphere is 4/3 pi r cubed. Our radius was 12 centimeters. We need to convert that to meters so we compare it with this. So in meters, that's 0.12. So if you plug this into your calculator, then you'll find that this density is 69.1 kilograms per meters cubed, which is obviously much less than this, which means that yes, it does float. All right. So our next question says, what is the buoyant sphere on the sphere? What is the buoyant force on the sphere described above? So the sphere is placed in the water. What is the buoyant force on it? Now you might be tempted to just plug it in directly to the formula, but that is a bad call. So first you should draw a free body diagram. So we have some water here, and we have a sphere in it. And because we found the density was less, we know that it's floating. So there are two forces on it. There's the force of gravity and the buoyant force. So if we use our normal coordinate system, where up is positive and down is negative, when we sum the forces on this sphere, we have the buoyant forces going up, so it's positive. We have weight going down, so it's negative. And as always, this is equal to mass times acceleration, but it's floating, and it's floating in still fluid. So the fluid's not moving at all. That's when these equations work. So that means its acceleration has to be 0, which means that these forces have to add to be 0. So if we arrange this, then our buoyant force is equal to the weight of our object. Our object had a mass of 0.5 kilograms. This is 0.5 times 9.81. Oops. And so this is what? 4.91 newtons. So this is the buoyant force on our sphere. Now notice, because it's floating, some of it is below the water, some of it is above. We couldn't just use our formula directly. Okay. So our next question says, we have a cube now with side length 1 centimeter that has a mass of 0.5 kilograms and is placed in pure water. Does it float? Okay, so we have to do the exact same thing. We need to find its density. So density is given by mass over volume. Its mass is our 0.5 kilograms. And it's a cube with side length, what was it, 10 centimeters? 1 centimeter. So the volume of a cube is the side cubed. So if we convert that to meters, this is 0.01 cubed. So if you plug this in, you get what? You get 500,000 kilograms per meters cubed. So this is clearly bigger than 1,000, our density of water, which means that this thing does not float, it sinks. Okay. Our next question says, what is the buoyant force on the cube? So the cube is placed in the water and it's sinking. Okay, because its density is larger. So before we just start plugging stuff in, let's draw a free body diagram. So our cube here is placed in the water and it's sinking. It still has the same forces on it. We have gravity going down, and we have the buoyant force going up. If we use our normal up is positive coordinate system, then when we sum the forces on our cube here, our buoyant force is positive because it's going up. Our weight is negative because it's going down. But this time it's not floating, it's sinking, which means that it is accelerating in the down direction. So this is not equal to 0 anymore. This is equal to our mass times our acceleration. Now we don't know what this acceleration is, so we can't do anything with this formula to find the buoyant force. So instead we'll use our formula directly. So we know the buoyant force is given by the density of our fluid times the volume of our fluid displaced times the acceleration due to gravity. This is the buoyant force. So an important thing to note is that these are for the fluid, not for the object. So this will be 1,000 because our fluid is water. And this will be the volume of our water displaced. Now, because our cube is completely underneath the water, that means the same amount of water equal to its volume has to be displaced. Now, for our sphere up here, that was not true. Part of it is out of the water and part of it is in the water, which means that if we tried to use the formula directly, we wouldn't know what volume to use because it's not equal to the volume of the sphere. But here, we don't have to worry about that because all of it is underneath the water. So our buoyant force then is our density of our fluid times the volume of our fluid displaced, which is the same as the volume of our cube, times the acceleration due to gravity. So this thing is what? This is 0.00981 newtons. Okay, so our buoyant force is extremely small because the volume of our cube is extremely small. We could also calculate the acceleration if we wanted to by calculating the weight of our cube, subtracting them and dividing by the mass. But whatever, the question doesn't ask us to do that. Okay, so time for long answer problems. So the long answer problems for this chapter will be based on Bernoulli's equation. So remember, Bernoulli's equation is very similar to an energy equation, except instead of mass, we have density, and we also have pressure, which acts similar to work. Okay, let's get into it. A 2.5 meter cylinder full of pure water that's open to the air on top is struck by a bullet 5 centimeters above its base, allowing water to pour out. With what speed does this happen? All right. So we have some container of water. It's 2.5 meters high. And there's a bullet hole in it near the bottom, and water is pouring out. Okay, and we want to know the velocity of this water. And this is a distance of 5 centimeters. Okay, so this is a Bernoulli's problem. So we'll use Bernoulli's equation. So Bernoulli's equation says that the pressure on one side of a pipe or anything where a fluid is, plus a term that looks very similar to the kinetic energy, plus a term that looks very similar to the gravitational potential energy, is a constant. So it's equal to the same thing at some point later in the pipe. Okay, so this is very similar to conservation of energy, like I said, but our masses are replaced with densities, and then we have the pressure here. Now here, we don't really have a pipe. We have this container of a fluid, so it works the same way. So we can use, as our two different places here in this pipe, we'll use the top and then the part where the water is coming out here. All right. So just like an energy problem, we need to figure out where we want to set y is equal to 0. So we can do that anywhere we want to, and we always get the same thing, but it'll be easiest to set this point to be y equals 0, because this term will then go away. And that means that our y1 is not 2.5 meters now, because that's measured from the ground. It's our 2.5 minus 5 centimeters. So that's 2.45 meters. Okay, now what about the pressures? Believe it or not, all the information to find both pressures is already given in the problem. Our problem says that the top of our container, the top of our cylinder is open to the air, which means that the pressure for that part must be the atmospheric pressure, that 1 times 10 to the 5th pascals. But where the water pours out here, it is also open to the air. So the pressure there must be the same. Okay, so we've already drastically simplified our stuff here. So we can subtract the pressure from both sides. Our y2 is 0. But we still have two things we don't know. We don't know the velocity at the top. We also don't know the velocity where it comes out here. So we have one equation, but two unknowns. So we need another equation. And that equation is our equation of continuity. So this equation, remember, tells us that all the water that's coming out of one side has to be leaving the other side. or whatever fluid that we have. Now for this one, we actually don't have these areas. The problem did not give us that. It only told us the height. So it didn't tell us the radius of the hole or the radius of the top or anything else, but that's okay. Because the idea is if you have a problem like this hole is extremely small compared to our opening here. So our area 1 is much, much larger than our area 2. And so we'll make the approximation that the velocity at our top here is actually 0. That's just because there's so much water here and there's such a small hole here, such little of it is coming out that it's not enough to actually make this actually go down, to make the water level change at all. Okay, so now we have drastically simplified our equation. This part can go away. This part goes away because it's the same as this. And this part goes away because that's where we set y is equal to 0. So if we rewrite our equation then, we have our rho g y1 has to be equal to 1/2 rho v2 squared. All right, so our densities cancel. We can solve for v2. It's plus or minus because we take a square root, but we were only asked for the speed, so we don't care about that. And our velocity is the square root of 2g y1. So this is actually very interesting. This is the exact same velocity that a regular object that's not part of a fluid would be traveling if it started from rest at this distance. So just an interesting little fact there. If we plug our numbers in, this is equal to 6.93 meters per second. So this is the speed at which, this is the speed at which the water is coming out of our hole here. All right. Let's move on to the next problem. So pure water flows through a pipe. One end of this pipe is circular with a radius of 10 centimeters and a pressure of 2.25 times 10 to the 5th pascals. And its center is 0.5 meters above the ground. The other end of the pipe is also circular with a radius of 2 centimeters with its center 7.4 meters above the ground. And the water pours out into open air at sea level. What is the velocity of the water at both ends of the pipe? So this is another problem, another Bernoulli's problem. That's very similar to the last one. All right, so we have a pipe. Let's draw it. So it starts off low, and it travels up some distance, and it also narrows. I did a bad job of drawing that, but I think you get the idea. So the pressure here is 2.25 times 10 to the 5th pascals. Our radius here is 10 centimeters. And the ground is somewhere. So the distance from the center of the pipe to the ground is 0.5 meters. And this distance to the center of the pipe is 7.4 meters. Okay, now when we're measuring height, we should always measure to the middle of the pipe for the same reason where if we had some body, we measure to the center of mass. If you just consider like the plane of the fluid here, then the center of mass would be at the center of the pipe, and water pours out here into the open air. And the radius here is 2 centimeters. All right, so let's write down Bernoulli's equation. Bernoulli's equation tells us that the pressure plus the kinetic energy divided by volume plus the potential energy divided by volume is a constant. Okay, let's do the same thing we did with last time. Let's set where y is equal to 0. And let's do that here, the lowest point of our problem. So if y is 0 here, that means that y1 is 0. And Y2 isn't 7.4 anymore because we're not measuring from the ground, we're measuring from here. So that means it's 7.4 minus 0.5, which is 6.9 meters. Okay, and we're looking for the velocity at both sides of the pipe, but we don't know P2, right? P1 was given in the problem, but P2 was not. But that's okay because our fluid flows out into the open air, which means it must be the atmospheric pressure. So our P2 is this 1.01 times 10 to the 5th pascals. So this is a very common trick in these problems. They don't tell you one of the pressures, but they do tell you that it goes out into the open air. So anytime that happens, that means that the pressure is going to be atmospheric pressure. Okay, so we can simplify our problem now because this is 0. All right, so we know everything here. We know the density of pure water. We know our height. We know both of these pressures. So the only thing we're missing is our velocity at this end of the pipe and our velocity at this end of the pipe. Okay, so this is one equation with 2 unknowns. We need something else to solve it. And so what is that thing? It's our continuity equation. So remember, this tells us that all of the fluid that goes through one end of the pipe also has to go through the other end. Now, both ends of our pipe have circular areas. So we know the area of a circle is pi r squared. Okay, so now we have 2 equations and 2 unknowns. So we know how to solve these. We can solve for, say, V1 in terms of V2 and then plug it in up here. So if we do that, V1 is R2 squared divided by R1 squared, our pi's cancel, times V2. So we can plug this in for V1 here. So if we do that, we still have our pressure here. Now our V1 is squared in our formula up here, which means we have to square everything. We have to square both of these radii and the velocity. So we have R2 to the 4th now, because R2 squared is to the 4th, divided by R1 to the 4th times V2 squared. And that's equal all the stuff on the other side. Okay, so now we have one equation and one unknown. We know everything here except for V2. So if we get V2 on one side and put everything else on the other side, then we have this. So I just kept this on this side, subtraction this to the other side. I'll put everything else on the other side. So we have this. So just factor the V2 out of this and this. Okay. Now we can divide by this ugly thing and then take the square root. So if we do that, we'll have it's plus or minus. We're asked not for the speed this time, but for the actual velocity. So the direction is going to matter. So it's plus or minus the square root of 2, the difference in the pressures, plus this thing, divided by the density times this thing. Okay, so it looks really ugly, but it's not too bad. All right, so if we actually plug our numbers in, then we'll find that our velocity V2 is 10.6 meters per second, and it's moving to the right. How do we know that? Well, if we look at our pipe way up here where I drew it, the water is coming in this side and leaving this side, which means on both ends, it is moving to the right through the pipe and then out the pipe on this side. And so we solve for V2. So that's the velocity of the water that's pouring out of the pipe here. But we still have to solve for V1, the velocity on this side of the pipe. Oops. All right, so now that we have V2, we can plug this back into our equation here. So our V1 is R2 squared divided by R1 squared times V2. And so if we plug in our radii, we'll find that V2 is 0.424 meters per second. And it is also moving to the right. Okay, so we found everything that we needed. Now, it might be a little odd to you that the velocity at this end is so much larger than this velocity, but that's because our pressure decreased by so much, right? Our pressure is over twice as much on this side than it is on this side. So if the pressure goes up, that means that the velocity on this side will have to go up to compensate. Now we also have this change in height here, which will help a little bit, but it's only 6.9 meters higher. So the velocity still has to take on a lot of this role. So the velocity coming out must be much larger than the velocity going in. Also, the area of this side of the pipe is smaller, which also means the velocity has to increase. All right. So the only tricky part here is remembering that anytime you have your fluid out in the open air, then its pressure has to be the pressure, atmospheric pressure. Okay. Now, chapters 15 and 16 won't have a lot of representation on the test, but there might be one or two short answer or fill in the blank problems about it. All right, so starting with our first question. A spring with spring constant 125 newtons per meter has a 0.25 kilogram mass attached to it, which is free to move on a frictionless horizontal surface. The spring is stretched by 5 centimeters and released from rest. What is the mass's energy? And what is the maximum speed? And what is the maximum distance the spring will be compressed? All right, so let's draw what's going on here. You have a spring with a mass attached to it, and it's free to move on this horizontal frictionless surface. All right, we stretched it back some distance of, what was it? It was 5 centimeters or 0.05 meters. So we stretched it. Let's use our coordinate system where stretching stuff is positive and compressing stuff is negative. So we started off with it stretched by positive 0.05 meters. Now we can always find the energy of some object by adding its kinetic energy and its potential energy. Now, because there's no non-conservative work here, the only work that's being done is by the spring. So there is no non-conservative work. This energy is constant. So I can calculate this at any point along its path. So what's going to happen is we stretch this thing out. It's going to come back in. It's going to stop at some point when it's compressed, and it'll keep moving back and forth like that forever. So at any point on this trajectory, the energy is always going to be the same. So let's calculate it where it was initially. So initially it was stretched by this 0.05 meters, and it was released from rest, so it had no kinetic energy at all. Now the potential energy for a spring is given by 1/2 kx squared. And so we were given our spring constant in the problem. It's 125 newtons per meter. And we'll have to use our maximum distance that it was stretched, since we're using the point at which the kinetic energy is 0. And so if we plug in our numbers, then our energy is 0.156 joules. So this will always be the energy that the mass has until something stops it from moving in its oscillation. Okay, the next thing you want to know is what is its maximum velocity? So we can use energy to find this out. So our energy is this thing, it's 0.156 joules, and it has to be equal to the kinetic energy plus the potential energy at anywhere along the oscillation. Now we want to know what its speed is when it's moving the fastest. Now it's moving the fastest at equilibrium, right? The energy is split between the kinetic energy and the potential energy. So it's the fastest when the potential energy is 0 and you only have kinetic energy. Okay. So at equilibrium, our x is 0. So this goes away. And so we're just left with 1/2 mv squared. We know our mass, so we can solve for our velocity. And it's given by plus or minus 1.12 meters per second. Now our plus and minus here is usually an artifact, right? We only want one of them and the other one is just something that the math gave us that we don't care about. But here the plus or minus is actually important. So what the plus or minus is telling us is at equilibrium, it could be going either direction, right? So it keeps moving back and forth like this. So at equilibrium, it could be moving in the minus direction, in which case the velocity would be minus 1.12 meters per second. Or it could be moving in the positive direction, in which case the velocity would be positive 1.12 meters per second. Okay, now the last thing you want to know is what the maximum distance that the spring will be compressed is. So we'll do the same thing. We'll start off with our energy. Now, when the spring is maximally compressed, the velocity is 0. And so we're only left with potential energy. And if we solve for our x here, we have plus or minus 0.05 meters. So this corresponds to the maximum distance that it's stretched and the maximum distance that it's compressed. So because there's a square in our formula for our potential energy here, it's the same energy whether the spring is stretched or compressed. And so when we solve this, we get two solutions, the maximum stretched part and the maximum compressed part. Now we were only asked for compressed, and we said in our coordinate system that compressed is negative. So the maximum distance that it's compressed is minus 0.05 meters. Okay. Now our next question says, what are the frequency, period, and angular frequency for the mass above? All right, so we learned a set of formulas to find all of these things. The frequency of a mass in simple harmonic motion, which is attached to a spring, is 1/2 pi times the square root of the spring constant divided by the mass. And so if you plug that in, this is 3.56 hertz. So in words, what this means is that there are 3.56 oscillations every second. So remember, hertz means 1/seconds. So this is 3.56 oscillations. So as it goes back and forth, it goes from its maximum stretch position to equilibrium to maximum compressed, back to equilibrium, back to maximum stretched. So it does that full rotation, that full thing, 3.5 times per second, a little over 3.5 times per second. All right, now the period is the amount of time that it takes for one oscillation to occur, and it's given by 1 over the frequency. So if we take 1 over 3.56, then we get 0.281 seconds. So this is the amount of time that it takes to get from one point into the oscillation back to where it was. So for instance, from maximum stretched back to maximum stretched. Okay. And the final thing that the question asked for was the angular frequency. So the angular frequency, to use the Greek letter omega for that, is 2 pi times the regular frequency. And so if we just multiply that together, we get 22.4, and it's measured in radians per second. Some people will write radian hertz, but I mean, that's kind of stupid. Radians per second is fine. Okay. So our next problem says, under what condition does an object engage in simple harmonic motion? So it's not just springs, other things can be in simple harmonic motion. And that's anytime the acceleration is proportional to minus the displacement. Oops. Or in other words, if you write this like a differential equation, it means the second time derivative of position is proportional to minus the position. Okay, this doesn't actually have to just be x. This could be an angle, like for pendula, or it could be something else. But anytime this is the case, then it engages in simple harmonic motion. And so notice the quintessential example, Hooke's law does look like this. So Hooke's law tells us that our force is minus some number, some spring constant, times x. So we know our force is given by mass times acceleration, as long as this is the only force on our mass. So if we divide by mass, our acceleration is minus k over m times x. And so it's exactly in this form. Our acceleration is proportional to minus our displacement. Okay. The next question is, describe what frequency and period mean for an object in simple harmonic motion. Well, we kind of already did, but frequency is the number of oscillations that occur per second, and period is the amount of time that it takes to complete one full oscillation. All right, next one. An object in simple harmonic motion has an amplitude A and an angular frequency omega. If at t equals 0, the object is at its maximum positive distance from equilibrium, what function can describe this motion? All right, so first off, we know that it needs to be sinusoidal, right? An object in simple harmonic motion moves back and forth. So if we plotted that versus time, it's going to have to be some maybe like this, or depending on the initial conditions, maybe like this, or whatever. It has to be some sinusoidal function. So this is position. So in other words, it has to be of the form cosine plus sine. So everything in simple harmonic motion is going to be something like this. These don't have to be the same. In fact, they shouldn't be. So let's call this speed. So these are just some real numbers. Okay, but our problem told us that at time equals 0, it's at its maximum position, maximum positive displacement. And so x at t equals 0 is the amplitude. So let's call that little a. All right. Now at 0, our sine is 0, so we don't have to worry about it. And so our x of t is our amplitude times cosine of omega t. This is because at 0, it's at its maximum position. If it started off at 0, then this would have to be 0. We would just be left with the sine. We won't worry about that, though. You can just always assume that cosine will describe any object in simple harmonic motion. All right. So that's it for chapter 15. On to chapter 16. All right, so chapter 16 is on waves. Our first problem says, sketch a plot of a wave and label the amplitude and wavelength. So waves, remember, are closely related to simple harmonic motion. So they have the same sinusoidal behavior. Now, depending on what we're plotting, what type of wave it is, you can have something different on the y-axis. But let's assume it's a transverse wave and our media is actually physically moving up and down. So this will actually be the vertical distance. This is the horizontal distance, the direction that the wave is actually traveling. And so it can start at maximum or it can start from 0 or whatever. It doesn't matter. They're all waves. So I'll just start like this. Okay. So this is a snapshot of a wave at one time. And we're supposed to label the amplitude and the wavelength. Well, the amplitude is the maximum distance from equilibrium. So it's this distance up to wherever the highest part of this peak is. So this is our amplitude A. This is also our amplitude A. It's the same as long as you take the absolute value here. You don't take the negative. Amplitudes are always positive. And then the wavelength is the physical distance from one part of the wave back to itself. So for instance, from crest to crest, remember wavelength is given by the Greek letter lambda. Or we could go from trough to trough, that's the same distance. Or we could go from 0 going down to 0 going down. That's also our wavelength. Any point of the wave back to the same point. They're all the wavelength. All right. So our next problem says a wave has a wavelength of 10 meters and a frequency of 200 hertz. With what speed does the wave propagate? So to find this, we'll have to use our wave speed equation. So the wave speed equation tells us that the velocity of a wave is equal to its frequency times its wavelength. So we know both of these. We said our frequency was 200 hertz and our wavelength was, what was it? Was 10 meters. So we just multiply 210. And so our velocity is 2,000 meters per second. I could flip this around and tell you any two of these and ask for the third one, but you know where. Okay, true or false? A wave carries the medium through which it travels with it. That is false. So waves carry energy and momentum, but they do not carry the medium with it. So for instance, in a water wave, the individual water molecules are not carried along with the wave. They stay where they are and move up and down and side to side, but they're not carried along with it. Okay, describe constructive and destructive interference. So interference is what happens when two waves occupy the same space. And if they are both positive, if some part of the wave, they're both positive and they add together, then they construct. That's called constructive interference. If one is positive and one is negative, then they destruct, and that's called destructive interference. All right, true or false? Two waves are traveling head-on toward one another and move past each other. The interaction changes the frequency of both waves. That is false. When two waves occupy the same space, the actual wave that you observe is just the result of adding their amplitudes together. But once they move past each other, they remain unchanged. They're exactly whatever the wave was before it encountered the other wave. Okay, a longitudinal wave is traveling in the x direction through a medium composed of particles constrained to the xy plane. In what direction do the particles move? So in a longitudinal wave, the actual disturbance, the way that the medium moves, is parallel to the direction that the wave is traveling. So because our wave is traveling in the x direction, our medium, or our particles that compose our medium, will move back and forth in the x direction. So they'll move in the positive x direction and then the negative x direction, but never in the y direction. Our next question says, a transverse wave is traveling in the x direction through a medium composed of particles constrained to the xy plane. In what direction do the particles move? Well, a transverse wave is a wave in which the particles that compose the medium move perpendicular to the wave. So since the wave is traveling in the x direction, the particles must be moving in the y direction. So they'll move in the positive y direction and the negative y direction, but never in the x direction. All right, and our last question, what happens when a wave is incident on a barrier between media? Some of the wave will be transmitted through to the next medium, and some wave will be reflected back and stay in the first medium. Okay, so I hope you guys like this. I hope it was helpful.